All right, so you're probably here because you want to get up to speed with some of the latest image generation breakthroughs, those really pushing the envelope, so to speak.
Absolutely. And this is a perfect example.
Right, so we're diving into a paper today called Regressive Image Generation Without Vector Quantization.
Yeah, a mouthful, right?
Yeah, it is a bit, but stick with us because it's worth it.
Oh, it definitely is. This paper is really asking a fundamental question.
Yeah.
Is this initial conversion to discrete tokens like really necessary for good image generation, with autoregressive models?
Yeah, because we've been doing that for a while, right? Converting images into these
Right.
tokens,
It's been the dominant approach.
like visual words almost.
Yeah, exactly. And the standard way to do this has been vector quantization or VQ.
VQ, right? So that's kind of like taking this rich continuous image and, kind of breaking it down.
Yeah, you're taking this continuous spectrum of pixel values and grouping them into a limited vocabulary of visual
It's
elements.
like a compression almost.
Exactly. It's a form of compression. You're essentially mapping parts of the image to the closest entry in this predefined code book.
But that mapping can be a bit lossy, right? I mean, you're losing some of the original information.
Precisely. That's one of the key points this research challenges. Even with advanced VQ techniques, there's always some degree of information loss when you go from that continuous representation to a set of discrete tokens.
So it's kind of like you're trying to paint a picture with a limited palette.
Yeah, a great analogy. You lose some of those fine predation details.
And this loss of detail can ultimately impact the quality of the generated image, right?
Absolutely. It acts as a bottleneck, limiting how realistic and detailed the final output can be.
So if we know they have an issue, why has this VQ approach been so popular?
Part of it stems from the huge success of autoregressive models in language processing, where the data words are inherently discrete. So applying that to images, it made sense to discretize them first.
Makes sense. But this paper is challenging that assumption.
Exactly. They're saying, hey, let's rethink this whole discretization step.
So what we're going to do in this deep dive is understand how they do it.
Yeah, dive deep into the method, see how they sidestep this discretization and why it's a potential game changer.
So it's like a shortcut to understanding this cutting edge research.
Exactly. We'll break it down into understandable chunks.
Awesome. So, okay, let's dig a little deeper into these problems with discrete tokens and VQ.
Sure. So as we said, VQ involves creating this finite set of visual elements, right? Like a visual dictionary.
Right, and each element is kind of like a representative for a bunch of similar pixel patterns.
Yeah, think of it as grouping similar patches of pixels together.
Okay, but training these VQ models, or tokenizers, I
Your
guess,
tokenizers, they can be tricky.
they're quite sensitive to how you approximate gradients during training.
Right, because you're forcing the model to choose from this limited set of tokens. The gradients, the feedback signals the model uses to learn can be a bit noisy.
Yeah, like the model is trying to figure out, okay, how do I adjust my parameters to get the output I want?
But with this discrete constraint, it's not always clear how small changes in the model's parameters will affect the output.
So it becomes harder for the model to learn effectively.
Precisely. And this can lead to unstable training and potentially a suboptimal vocabulary of visual tokens.
Right? Like the model might not learn the best possible representation of the visual information.
Exactly. And remember that initial step of quantization where we lose some of the image's essence?
Yeah, the compression,
Well, that loss can really limit the autoregressive model down the line.
like a chain reaction almost.
Yeah, even the best reconstruction from VQ won't perfectly capture the original image.
So you're starting off with a less information-rich representation.
And that's the bottleneck they're trying to overcome.
Got it. Okay, so now for the really exciting part, the core of their proposed method.
They essentially ditched the whole discrete token idea,
Yeah,
work directly with continuous representations of the image.
bold move. So no more forcing things into a limited vocabulary.
Nope, it's a radical shift.
But that presents a challenge, right? How do you model probabilities with continuous data in an autoregressive way?
That's the million-dollar question. And this is where their key innovation comes in.
Diffusion loss.
You got it. They leverage the power of diffusion models, which are known for their ability to model these complex probability distributions.
Right. Diffusion models are all the rage these days in image generation.
They are. But here's the twist. Instead of applying diffusion to the entire image at once,
Like how it's typically done.
they use it to model the probability distribution of each individual token.
Wait, so each continuous token gets its own diffusion process.
Exactly. That's the brilliant part.
Interesting. Okay, so walk me through how this works practically.
Okay, so you have your autoregressive model, right? It's still predicting things sequentially.
But instead of predicting a discrete token, it predicts a continuous vector.
Yes, they call this vector Z.
Okay, Z. And this Z acts as a guide for another neural network.
Right, a smaller network called the denoising network.
Denoising network. What does that do?
Well, imagine you take a continuous token and add noise to it over multiple steps.
Okay, like gradually corrupting it.
Right. The denoising network is trained to predict the noise that was added at each step.
But here's the key. It does this based on the z vector and the current noise level.
Exactly. That's the conditional part.
So z's is like providing context for the denoising process.
Precisely. And the diffusion loss measures how well the denoising network can predict the noise.
So the better the denoising, the better the z vector must have been.
Right, because Z needs to contain all the information necessary for the denoising network to reconstruct the next token.
Yeah, like it's guiding the reconstruction process.
And the paper has a helpful diagram, figure 1, that visualizes this whole process.
Oh, cool. I'll have to check that out later. So essentially, they've found a way to use diffusion to train this autoregressive model on continuous data.
Without ever needing discrete tokens.
Really clever. But they didn't stop there, did they?
No, they took it a step further with this idea of masked autoregressive models, or MAR models.
MAR models, right? I've heard of those. They're like a more general form of autoregressive models, right?
Exactly. They can predict multiple tokens simultaneously and in a more flexible order.
So instead of going strictly left to right or top to bottom,
The model can predict tokens in any order,
kind of random.
right? It's like selectively filling in missing pieces of a puzzle.
Interesting. And this ties in with other cool stuff like Maskit and Mage,
Those are other generative models that use this masking idea.
right? So how does attention fit into all this?
Well, even bidirectional attention, which allows the model to look both forward and backward in the sequence.
Like in those masked autoencoder models.
Yeah, it can be used in this MAR framework.
So the model has a more holistic view of the image.
Exactly. It can learn richer relationships between different parts of the image.
Okay, I think I'm starting to get the big picture here, but let's talk about why this is also important.
Well, the most obvious advantage is that you get rid of that pesky VQ tokenizer.
No more quantization, no more loss of information.
And that potentially leads to higher quality images with fewer artifacts.
Plus, it seems like diffusion loss is pretty flexible.
Oh, it is. They show that it can even be used with existing VQ models.
By applying it to the continuous representations before quantization.
Right, like a performance booster even for those models.
Interesting. And it works with different types of tokenizers, too.
Exactly. They tested it with things like KL8 and consistency decoder.
All right, so they put this to the test on ImageNet, right?
They did, and the results are really impressive.
Tell me about it.
Well, they consistently get better image quality as measured by the FID score.
FID score lower is better, right?
Yes, lower FID means more realistic images.
And they saw significant reductions compared to using the traditional cross-entropy loss.
Across different model architectures, too.
That's convincing. So not just quality, what about speed?
Oh, their MAR model with diffusion loss is fast.
How fast?
They reported generating images in under 0.3 seconds per image.
That's crazy fast, especially for high-quality generation.
Right. It's really efficient.
And they have a nice figure 6, I think, that shows this speed accuracy trade-off.
Yeah, it compares their method to other state-of-the-art models.
So they didn't just make it better, they made it faster, too.
Exactly. A win-win.
Okay, so what about those ablation studies? Did they tinker with different parts of their method?
They did. They found that the denoising MLP doesn't need to be huge to be effective.
Good news for efficiency.
And around 100 diffusion steps seems to be the sweet spot.
Not too many.
And they even experimented with a temperature parameter.
Like in language models?
Exactly, to control the diversity of the generated images.
Okay, cool. So zooming out a bit, what's the big academic takeaway here?
Well, they've essentially combined two powerful ideas, autoregression and diffusion.
In a way that hasn't been done before.
Right, they're using diffusion not to generate the image directly, but to train an autoregressive model on continuous data.
And it really challenges our assumptions about autoregressive models.
Shows they can handle more than just discrete sequences.
So it's not just about image generation, it's about broadening the scope of these models.
Exactly. And the authors even suggest that this could be applied to other types of data.
Like audio or video.
Yeah, continuous data in general.
That's exciting stuff. So for our listeners, the key takeaway is this.
You don't need discrete tokens to do high-quality autoregressive image generation.
Diffusion loss makes it possible to work directly with continuous representations.
And that leads to all sorts of benefits, better quality, faster generation, greater flexibility.
It's a real paradigm shift. So here's a question for you to think about. Could this approach revolutionize generative modeling for all kinds of continuous data?
Yeah, is this the beginning of a new era where we move away from this reliance on discretization?
It's definitely food for thought. If you want to explore this further, be sure to check out the paper itself.
Yeah, it's on ArcC. They identify as 2406.11838v3.
And they also have the code available on GitHub.
We'll link to both in the show notes.
Awesome. Well, this research really does open up some fascinating possibilities.
It's a testament to the power of combining different ideas in creative ways.
And it makes you wonder what other breakthroughs are just around the corner.
Right. What other assumptions are we taking for granted that we might need to rethink?
Thanks for joining us on this deep dive, folks. It's been a pleasure exploring this cutting-edge research with you.
Always a pleasure.
Until next time, keep those minds curious and those imaginations fired up.
Absolutely.
See ya.